Okay, welcome back everybody. This is our third lecture in our contaminant transport chapter, and today we will start reactive transport. So we'll start looking into those plumes and different contaminants and how different substances, different compounds travel at different velocities essentially. Okay, so last time we looked at transport equations, so solutions to the differential equations that we did a couple lectures back. And this is the fundamental solution right here, which again is a Gaussian solution. It's a Gaussian curve or a bell curve that you have a representation here at the bottom showing you the amount of data within 1 and 2 standard deviations. And if you remember last time, right, 2 sigma, this is a sigma that looks like a tau, but 2 sigma is sort of a very important number for transport because that allows you to find the dispersion coefficient, right? So again, I invite you to go back to last lecture, but this is the fundamental characteristic of a bell curve that we use to calculate dispersion coefficients. And finally here on the right hand side, right here you can see how this bell curve, this fundamental solution is plotted in space and time, right? So space on the x-axis, concentration on the y-axis, and then finally time, on the third dimension. So if you have a pulse injection, a delta function as the initial condition, then over time the dispersion will just spread that pulse away. Okay, and again the dispersion is basically what makes this spread out over time. Again, related to, of course, the bell curve here and here. Okay, so that was the quick review from last time, and today, finally, we want to know what happens when we have different compounds in the mix. So this intro, again, this is taken from Feather, essentially, and a lot of the illustrations from today are from Feather per usual. And of course, solids dissolved in groundwater can be removed by a number of processes, right? So the first one, the one we'll see today, is sorption, right? So they can sorb to surfaces of the soil matrix or the formation matrix, right? Grains in the aquifer. For organic compounds, we'll talk about them a little bit at the end, but they can sorb, on organic carbon. So if you're in a soil, a lot of organics are going to stick to organics, and then they'll have retardation as well, or they'll be slowed down. There can be chemical precipitation, right? So if you have a salt, for example, that starts precipitating, then it's removed from the plume. Degradation and oxidoreduction are aspects we'll see on the next lecture, and then finally radioactive compounds, right, can just decay at their own pace, so they just disappear. So again, all those chemical reactions essentially remove mass from the contamination. And again, today we want to pay particular attention to sorption, right? So sorption basically is a process where molecules will stick to the surfaces of the soil matrix. Thereby, they're removed from the moving plume, and eventually they can be re-released from those surfaces, right? So it's typically a reversible process. So that essentially the mass is slowed down, right? So we'll see today how that works, but essentially, if you have a molecule that sticks to a particle of soil over a mineral and then is released later, right? Then it starts moving later, so the overall effect is to slow down the contamination. Again, biodegradation and radioactive decay can decrease the concentration, and that's the object of next week's lecture. So again, down here is retardation. You can see the water at the top, and then more and more, retarded species or delayed species. So if you have, again, an initial pulse, the water is moving this fast, but then different compounds move slower relative to each other. And here on the right, this is the decay. So you can see here we have missing mass, right? So it's been degraded, so it moves at the same velocity as the water, but now mass is removed and we don't find it. Okay, so diving into the sorption aspect of transport. So again, this is this first equation on the left here. This is your transport equation from last time, so advection dispersion, but now we have an additional process, which is basically the retardation, right? And importantly is that last term ds dt, right? So S would be the concentration of the sorbed species, right? So again, S would be a concentration in mass per mass, okay? So this is different from what we've seen before, because again, if you want the concentration of something that is stuck onto a grain, onto a mineral, now the concentration has to be, mass per mass of mineral, right? There's no volume of water or volume of fluid because obviously it's a solid. So now we're dealing with concentrations in mass per mass. And that's why you have that that factor here that includes density, right? So this is mass per volume, and this theta is the porosity. All right, so theta here really should be porosity. I mean, it's the same thing, but theta is really the saturated content. So if we did like Vadose zone hydrology, right, theta is a more general term than porosity. But if it's a saturated aquifer like the ones we've studied in this class, then theta is basically the same as porosity. Okay, so again you have density, and this is because now our concentration is in mass per mass. So if we wanted mass per volume, then we would need to know what is the bulk density of this aquifer. So now when we look at this, the units are consistent, but we have the concentration of the adsorbed substance in mass per mass. Now, one way to transform this equation with, into a retardation factor is to look at the chain rule, right? So here on the right-hand side, so I extracted this term right here and just rewrite it the same, but now extracting that dc dt so that we have the same expression that we have on the left-hand side, right? And now we can see that in the equation now we have ds dc appearing, right? So again, the change of sorbed species per change in bulk concentration, right? So this is really intuitive because that's what we call a partition coefficient. But if you think of what that is, right, it's if you have a plume of a contaminant passing through a formation, the higher the concentration, the more sorbed species you have, right? And then later on, when we have clean water basically coming through, and most of the plume, most of the mass is gone, and now we have at the tail we have, let's say, clean water. That clean water is essentially rinsing or cleaning up, right, the rest of the rocks that still have a bit of sorbed stuff, right? So it makes sense that the amount of sorbed concentration, the amount of sorbed material should be proportional to the concentration in the plume, right? And again, this is what we call a partition coefficient. And literally, if you look at the etymology or the meaning in English, right, we're just partitioning that plume into, some dissolved stuff, that's C, and some sorbed stuff, that's S, okay? Okay, so now we can reshuffle all of that, right? So now we have dc dt. So if we replace, this whole ds dt by the expression on the right hand side, now you can see that we can shift everything to the left, right? So now we have something dc dt here, right? Blah, let's call this whole thing blah. So this is blah here, right? So blah dc dt. Now we can shift this on the right hand side, and we can see that we have dc dt. We can factorize dc dt out, and now dc dt is going to be factor 1 plus blah, right? And this is what's here. 1 plus rho over theta, again, theta or eta, like porosity, rho over porosity times Kp, partition coefficient. So this is what we have here. Now this whole bit here that is the factor of dc dt, we can just call that R and call this a retardation factor. So now you can see that, after this bit of math, we have a very easy, simple solution, or simple equation, I should say, that is pretty much exactly the same as before, except now we have a retardation factor in front of it. So you have it here at the top, right? The retardation factor. So now after this bit of math, you can see that basically we have exactly the advection dispersion equation from before, and then there's a retardation factor, whatever that is we just saw, but there's a number here that just modifies dc dt. An important aspect to understand here is R is a factor, so it's obviously dimensionless. If you shift it back to the right hand side, right, now you can see that the reactive dispersion coefficient is d over r, and the reactive advection or velocity is u over r, right? So if I shift this to the other side, then we have dc dt equals d over r minus u over r. So all retardation does really is modify our velocity and dispersion, right? You divide this by r and you get the actual, reactive or retarded velocity and dispersion. So very simple, and you can see the effect here for a pulse injection after some time. So this is 1 week, 1 month, and 3 months, after an injection, and you have the code. You'll have the code in your folders, and I'll show it in a minute. But you can see that basically what happens is the retarded species is just, slower to reach some location, right? This is, again, this is time here, so this is 7 days, 30 days, and 90 days. And here the velocity is like 1 meter per day. So you can see that the mean time of the conservative tracer is just the number of days, basically, because it's 1 meter a day. And here, but then at the same time, right, the reactive tracer is not as far, right? So it's going slower, basically. At 90 days, it's only partly through the transport. Here on the left-hand side, you have what we call the isotherms, and this is an important term for sorption. We'll talk about those in the next few slides a lot. But for a linear sorption, and I'll make a distinction in a minute, but again, for a linear sorption, by definition, we've seen that KD or P partition coefficient, or this is KD is for, I can't remember what the D stands for. Anyways, it's the same as the previous one, right? So we've defined it as the concentration, the change in sorbed species per the change in bulk concentration in the fluid, right? And if it is linear, right, because the definition is this that we gave before, this is basically just the slope of, and again, C star here equals S. This is just a different convention. I put S to make the different, to really emphasize that this is the sorbed species, but in the feathered, he uses C star for the same thing, right? So anyway, so if we take a plot of the sorbed concentration versus the bulk concentration, so the concentration in the fluid, now you can see that this plot's on a straight line because it's linear, right? And the slope is KD by definition, right? Just like we've seen before. So if we have this data, then we can just take the slope and know what KD is, and obviously rho and theta, or the porosity and the bulk density, should be known. So now we have everything to actually calculate the retardation factor. Okay. And again, this is the same plot as before, right? Where we can see, so here I'm putting the code so I can emphasize how easy this code is, right? This is what I call PDF, is just the solution to the advection dispersion equation, right? ADE, right? So you can see that C at T equals, if you remember, m over square root of 4 pi dt exponential minus blah, right? So this is our fundamental solution that we wanted to remember. And you can see this is just the MATLAB version, right? So now m is 1, just if we make it a PDF, right? So it's just 1 over square root of 4 pi dt exponential minus blah, right? So this is just the function. So all I did here is for a reactive solute, or for sorption, right? All I do is divide the velocity by the retardation factor, divide the dispersion coefficient by the retardation factor, and then run the exact same equation, right? But with those modified velocity and dispersion for the reactive. Right? So the blue lines are just, the original velocity and dispersion, and those green lines are the modified, divided by R velocity and dispersion. And that's really all it is. If you have linear retardation, you just have that retardation factor, you just plug it in, and that's it. That gives you directly, the slowing down of the plume compared to the water, compared to the conservative transport, which is in blue here. Okay. Now, other illustration, right, of what retardation does in other boundary conditions, if you will. So right now, I've just illustrated with that simple pulse initial condition. We've seen last time when you have a sustained source, right, or a front moving, right, you can see that the difference in arrival time, again, is just the same as the pulse, but just with a different front here illustrated. So this is for a square input, basically, or continuous input. And you can see again that the non-retarded species is much further out, right? So this would be distance now, right? So the front is much further out than for the conservative, for the water, basically for the conservative species than it is for a retarded species. Retarded species, if you will, you can see here down in that illustration. For example, this, this middle plume here would be for the retarded species, right? And something that is not retarded, so again, this is pretty approximate, but, right, so this R, and then this outside here, no R, right? So again, this is now in space, right, X and Y, right? So in space, you can imagine the retarded species are just being, less dispersed and less fast or slower. And the less dispersed is a little bit, is not as intuitive as the slower motion, right? So it's less dispersed, again, because some of it is zorbed, right? So if you're a molecule and you're zorbed onto the matrix, now you can't disperse, obviously, right? You're stuck there. So that's really the effect on dispersion is really because of that, being stuck, basically. An amount of mass is like literally stuck and not dispersing at all. So the ensemble average, the mean dispersion is less, right? There's less material actually, doing the random walk, if you will, or moving away because, again, some of it is stuck. Here on the right-hand side, you have examples of organic compounds being retarded, and you can see that different compounds have different, retardation factors, basically. So the water, again, is up in front, and again, this is now in X, right? So this is in spatial coordinates, like that's space. So if the water is out in front, so this is the same as this left-hand side front, if you will, right? So if you have, this curve for water, different compounds. So acetone is retarded a little bit, but not much, right? And you can see that different compounds have different retardation factors, and trichloroethylene here is very much retarded, very tiny and very stuck there. Okay, so in real life, we don't really usually have those linear isotherms that we've seen before, but what happens is we have non-linearity of the sorption. The reason is, if you look at these linear isotherms like we had before, you can basically have infinite mass sorbing onto a finite amount of sorption sites, right? So if you think about it, like at high concentration, so at high bulk concentration in the plume, in the water, you should have, some amount of sorbed material. Now, if you increase the concentration a lot, right, at some point you saturate all your minerals. So once all your minerals are saturated, right, it doesn't really matter how much more mass or how much more concentration you have in the bulk, because everything is saturated, they can't just take any more, right? So there's a saturation process going on that is not accounted for by those linear isotherms, and that's why in reality, in real life, we almost always observe those non-linear processes, right, where, again, at high concentration, there is proportionally less, right, of the sorbed material, right? Again, because there's only so much we can stick in there. This is an example of, a Paolo basically isotherms. This is called the Freundlich Isotherms. There's a couple that are common. There's different things that you could do, but this is just as an example, right? So let's say we have a parallel relationship between the sorbed amount and the bulk concentration. Now you can see here on the right hand side, obviously for a parallel, right, if you log the both axes, right, log plot, you get a straight line, and now the slope is n and the intercept is log k. So again, if you have that kind of data, you can just log, extract those two parameters, and now we can finally calculate our retardation coefficient. But now, of course, right, because again, ds dc, right, so because the partition coefficient is by definition the differential of the sorb versus the bulk, right, when we differentiate that parallel thing, right, we get this n minus 1 here, and finally, so here this is rho, really, that should be rho, that's just the feather writing. But anyway, so you can see that it's a different partition coefficient, so this was the linear one for, so you can compare. So now this is not true anymore, but we have this new thing. So if we have the data, again, we can just, measure n, measure k from the data, and then rho and theta are the same. So you can see that this is a slightly different retardation coefficient, but at the end of the day, we still have some retardation coefficient, right, that we can just plug in, and then the result is the same, that it is rescaling your dispersion and your velocity, essentially. Now, what is the effect of that, right? So we've seen before the effect of linear retardation is just to literally, slow down the transport. Here you can see that for nonlinear process, it's a little complicated because, again, the retardation basically depends on the concentration, right? So you can see here we have the appearance of long tails, and again, this is that process that I talked about before, when we have that clean water flushing out the system, towards the end. Well, now because it was nonlinear, right, you have more mass that is still hanging around, after a long time. So not only there is a change in the timing of the transport, but now we have a reshaping of the plume that is not, obvious, right? So we're basically creating those long tails in transport, those late time elution that weren't visible for linear isotherms. So really here it gets pretty complicated pretty fast. Well, instead of just shifting the transport in time, now you're actually reshaping the transport. So now so let's say, for example, these were pathogens, right? Cryptosporidium, for example, where very, very low concentrations can be fatal, basically, or very dangerous for public health. Well, now the risk is extended in time for a long, long time, right? So now instead of after a few days you're done, well, now maybe it's a few months because you have that lingering concentration that is coming out of that aquifer, literally forever, basically. So again, nonlinear transport or nonlinear isotherm, nonlinear sorption, pretty tricky business. Okay, so other processes that can complicate sorption processes. Here on the left is essentially a dual or two-domain, linear isotherm. So it looks like a nonlinear, like just the one we've seen before, right? But here, if you look at this data, it's more like two different regimes with a regime shift in between, right? So this first one here, let's call it KP1, and then the second one here, let's call it KP2. Okay, so if we think of it, right, instead of being due to just nonlinear sorption into one compound or one mineral in the soil, now we can have two different surfaces basically having two different behaviors, right? Two different linear sorption isotherms. So each mineral surface is different and then expresses, different trends. So that's another example. So if you think of natural formation, obviously they're complicated, right? It's not like simple one surface or one compound, one mineral. It's actually a bunch of different minerals and organics, and the whole matrix is complicated, especially soils, for example. So you wouldn't expect things to behave, linearly and kind of simply. So this is one example of a still somewhat simple two-surface sorption, problem. Here on the right-hand side, this is something I've shown before, right, with different organics. being retarded more. So the problem with organics, and I'll just say a few words, but we could do a whole chapter on this, obviously. So organic compounds are essentially made of carbon, right? And carbon sticks to carbon, right? So organics stick to organics. Think of oil and water, right? They don't mix, or oil and vinegar, right? They don't mix. So organic compounds tend to be attracted to other organics. So especially in soils, for example, if you have, so the amount of retardation for an organic pollution, and these are very important because all gasoline products, right? All those are organic pollutions, and when they travel through soils, their retardation will be conditioned or will depend on the organic content of the soil itself, right? So the more organics you have in the soil, the more retardation of those hydrocarbon compounds you'll have. So this is really, really important. And again, there's a whole, obviously this is really important in engineering and remediation, so we could do a whole chapter on this. I'm not going to go too much into it, but just remember that basically the retardation factor for organics depends on the organic content of the formation. Okay, and finally, just sort of to bring this back to what I do for a living, I guess, what I do for research. This is an old paper of mine showing the effects of hyporheic reactive transport on breakthrough curves. So again, hyporheic is what is basically groundwater surface water exchange. So the hyporheic zone is that zone around streams and rivers in the sediment, right? So there's obviously rivers flow in alluvium a lot of the time, and there's an exchange of surface and groundwater at the interface there, right? So groundwater comes into the river, but then the river also kind of contributes water to that hyporheic zone, to that zone just around in the sediment, just around the streams and rivers. Now here is a couple examples, so you can sort of recognize those pulse, right? The sigma, or the dispersion, I should say, the velocity. Let's call this dispersion. So you can sort of recognize that Gaussian bell-shaped curve on a log-log plot. But then here at the bottom is really the impact of that hyporheic zone, basically, of that water that went into the sediment, right, and then back out. So in the sediment, it goes a lot slower, obviously, than the river flowing by. So in the sediment, it goes slower, and this is why we have those tailing behavior, basically, at late time, because this is some water that went into sediment. Now, inside the sediment, what can happen is, retardation can happen, right? And so this plot here just shows, different compounds for different retardation factors. So imagine the water is that red line now, and you have different compound with more and more retardation. Now they're going to come out, later and later and later. And this is what you see here for these different curves. And same thing here for a different. So if the water is, up top here, if this was water, now the retarded compound come out of this sediment below the stream, later and later and later. And that's really the point I'm trying to make here, is that those, there's a lot of real world applications that you wouldn't think about for retardation that are really important, right? So a lot of Superfund sites have, compounds that are stuck there because of retardation, that are stuck on the matrix, if you will, like that, absorbed, onto those minerals or organics in that formation. And the question to the environmental engineers essentially is, how can we get them out, right? And what can we do to help? Or sometimes, it's the opposite, where you have a plume of a pollutant that is moving through a formation or through an aquifer, and you'd like to slow it down, right? So sorption can also be used in remediation to sort of, what can we do to slow it down? Basically, can we add something to this formation to precipitate, to sorb, to eliminate this pollution, or slow it down at least, so we can get mechanical solutions downstream at some point. Okay, finally I'll conclude on this. So next time I'll do other types of reactions, so degradation, redox reactions, and this is an example where you have a plume, right, and you can see that depending on where you're at physically, like spatially in the plume, you have different sorts of reaction. And this is your sort of standard, right, redox fronts. So you have, oxygen is used all the way out, right? There's oxygen here, so this is the first thing that goes, basically, that we respire. But then when this oxygen is gone, right, we get the oxygen basically from other compounds, and this is like denitrification is the next one here. So we get the oxygen basically from the nitrate, and once we remove the oxygen from the nitrate, that gives nitrogen gas, right? Here you have manganese oxides, right? So once the nitrate is gone, right, there's no more nitrate, well, we go down the ladder, right? So now we use manganese to get our oxygen. Now the oxidative power, so now there's no more oxygen, basically no more oxides. So now we have to start reducing, other stuff. So this is iron, and iron is a typical one. I really like the iron example because when you see a spring, a groundwater spring, so when you walk in a wet forest somewhere, right, and there's a seepage of groundwater basically that you can sort of tell by how swampy that place is, you can actually see the iron precipitate as iron 3. When it comes out of the ground, it's usually reduced, so that would be iron 2 there, right? It's reduced, it has that gray or green-gray sort of color, and when it comes out to the atmosphere, right, it gets in contact with the air, so the oxygen in the atmosphere, and all of a sudden it gets oxidized into that rust, right, into that red color, and you can literally see the red iron precipitates around those little springs and stuff. So this is a pretty interesting phenomena. So this is something we'll describe some more in the next lecture, where we'll get into degradation and decay. All right, thank you very much.